Right, so welcome to part 3 of our tutorial about the expectation maximisation algorithm. Today we're going to look at how we apply it to a Gaussian mixture model. So this was the first contextual example that we looked at in video 1. So if you've forgotten anything about it, you can go back and look at it. Stated very briefly, Gaussian mixture models it's a clustering procedure. So if we have some data, we drew something like this. We want to cluster that data or work out what clusters each point belongs to. And we have a hypothesis, which is that each of these data points is generated by a two-step procedure, where step 1 is that we pick, in this case, one of 3 Gaussian distributions. And then in step 2, we generate a sample from that Gaussian distribution. So we said that, let's say this was Gaussian 1 and it had mean 1, covariance matrix 1. This is Gaussian 2 with mean 2 and covariance matrix 2. And then this is Gaussian 3 with mean 3, mu 3 and covariance matrix sigma 3. And we said, okay, fine. In step 1, when we pick a Gaussian, the probability that we pick the kth Gaussian is given by pi k. Okay. So in this particular example with 3 Gaussians, the parameters that we had to find were mu1, mu2, mu3, sigma 1, sigma 2, and sigma 3. And we also needed to find pi 1, pi 2, and pi 3. So they made up our theta. And we also had latent variables, z's. We said, okay, if we consider the nth point, say xn, let's say next to it has something called zn. And basically, every element of zn is equal to 0, except for one of them, which is equal to 1. If the kth element of zn is equal to 1, it means that xn has come from the kth Gaussian. So if xn has come from the second Gaussian, as an example, then zn would be equal to 0, 1, 0. Okay, so that's our Gaussian mixture model. We then went on to show that if you do the expectation maximisation algorithm, we use it to find optimum parameters, theta, where the optimum is defined as the theta that maximises the likelihood and therefore the log likelihood. So it's the theta that maximises the probability of witnessing our data. And then we showed that if our current best guess of theta is theta superscript I, and that we calculated this thing, so the expected value of log p of x and z given theta with respect to this posterior distribution over z, and then we maximise that thing with respect to theta to realise the theta I plus 1, then theta I plus 1 has to be either equal to or better than theta I. So it means that if we follow this expectation maximisation step and we repeat it again and again, loosely speaking, our estimate of theta has to get better at each iteration before it converges. So today we're going to look at how that's applied specifically to a Gaussian mixture model. Right, so the first thing we're going to do, to be more general, is say that we're not just going to look at 3 Gaussian distributions. We're going to say we could have capital K Gaussian distributions. Gaussians, okay? So that means that the parameters we need to find, theta, now includes the mean vectors of all K Gaussians, the covariance matrices of all K Gaussians, and also what we called the mixture proportions of all K Gaussians. And we're also going to say that we have capital N data points. So that means that our capital X is equal to capital N different data points. So each one of these is a black dot on the picture we drew earlier. And corresponding to each data point is a latent variable. So we also have N latent variables. Okay, so now the first thing we're going to do is this expectation step. So we're going to begin by trying to write down probability of x and z given theta. And in fact, we'll start slightly simpler and we'll try and work out what is the probability of xn, so just one of these, and zn given theta. And we know we can write that as the probability of xn given zn and theta multiplied by the probability of zn given theta. Now remember that we use Zn to represent which Gaussian was used to generate Xn. So Zn will be equal to 0 everywhere, so every element of Zn will be equal to 0, except for 1. So for example, if Zn k dash is equal to 1, then it means that it's this Gaussian that was used to generate the point Xn. So what we're going to do now is going to write that this is actually the product over all Gaussians, so from k equals 1 to capital K. And we're going to say that's the product of, so we've got the probability of xn given that znk is equal to 1, and theta, and then the probability that znk is equal to 1 given theta. And we're going to put that all to the power of znk. Okay, so here, if znk was equal to 1, then that means xn came from the kth Gaussian. So this is a normal distribution, random variable xn, mu k, and covariance matrix sigma k. And also this is equal to just pi k, our mixture proportions. So we end up with this product over k equals 1 to k, capital K, with a normal distribution with mean mu k, covariance matrix sigma k, and then pi k, all placed to the power of znk. So, for example, if we do have this case where znk dash is equal to 1 and everything else in zn is equal to 0, then what we're doing is, if k is not equal to k dash, then we're just multiplying 1s together. And then when we do reach k dash, this is equal to 1, and we're just left with this expression here. So hopefully you can see that for this particular case, once we'd multiplied over all our different Gaussians, we'd be left with normal distribution xn for mu k dash, covariance matrix sigma k dash, multiplied by pi k dash. Okay? So that is our probability of xn and zn. Then finally, we note that the probability of generating a particular value xn is independent of all the other x's. Likewise, the probability of generating a particular vector zn is independent of all the other z's. So the probability of witnessing all of our data is this. So I'll just copy this. But now we're multiplying over all of our data points. So from n equals 1 to capital N. And then finally, what we actually need is the logarithm of this. So we know that log probability of all x and z given theta is equal to summation over n equals 1 to capital N, summation of k equals 1 to capital K. Then we take the logarithm of this, so we end up with z n k multiplied by the log of our normal distribution with xn as the random variable, mean mu k, covariance matrix sigma k, multiplied by our mixture proportion, which is pi k. Okay. So now we have an expression for this log probability of x and z. So now our final step of the expectation part of the algorithm is to take the expectation. So specifically what we're looking at is the expectation, and I'll say specifically with respect to, so with respect to the probability of z given x and our current best guess at our parameters, which is theta I. Of this thing, okay? So our log probability of x and z given theta. And that will be equal to, well, we've only got one z in here. So that will be equal to, again, we're going to use this notation here. So we explicitly say it's the expectation with respect to probability of z given x and theta I. So now that's going to be applied to z nk. And then all we've done is we're just going to write the expectation here, so over those z, so everything else remains the same, so it's still summed over n and k. It's still going to be multiplied by this thing here. Okay, So this is what we're going to try and maximize with respect to theta. But you can see that before we do that, we need to work out what this thing is going to be. And so that's what we'll do in the next step. Right, and we can do that using Bayes' theorem. So what we're going to do now, we're going to write down we're just going to say, okay, probability of, so we're going to try and write down this thing here. Let's just say, what's the probability that Znk is equal to 1? Given xn and theta I. Whoops. Okay, like I say, we're just going to write down Bayes' theorem, so that is equal to the probability of witnessing xn, given that Znk is equal to 1, and then still conditional on our parameters being fixed to theta I. And then the prior is just probability of Znk being equal to 1 given theta I. And that will all be divided by, so each of these data points must have come from a Gaussian of some kind. So what we need to do is we need to make sure that if we take this thing and we sum it over k equals 1 to capital K, so if we put that into here, and then that will be all equal to 1, okay? Because it has to have come from one of the Gaussians. The point xn has to have come from one of the Gaussians. So we just need a normalizing constant which will ensure that that happens. So I'm going to sum over, I'll say a k dash rather than a k, just to avoid confusion. It's equal to 1, capital K. And basically it's all this stuff, but with the k's set equal to k dashes. So I'll put that there. I'll zoom in a bit and I'll try and so get rid of that, get rid of that. Because that is now a k dash and that is a k dash. Okay, good. So that is the this distribution over z. So we've got this thing here. Now we need to calculate what the expected value of Znk will be with regards to this probability distribution. And actually this is quite easy. I'm sure you'll be glad to hear, because you can say, okay, the expected value of Znk is equal to, and so we sum over all the possible values that Znk can take. And the first one it can take is 0. So it would be 0 multiplied by the probability that, so you can see this is going to disappear, but I'll write it out in full anyway. Znk is equal to 0. Given xn and theta I. Okay, plus the other option is that we can have z and k being equal to 1 multiplied by this, just going to copy this. Okay, so that's a z and k equal to 1 times the probability that z and k is equal to 1. And so actually, what you can see is that the expected value of z and k is actually equal to the probability that z and k is equal to 1, which is quite convenient. That's what we've written here. So now the final thing we need to do is, right, okay, so that is all equal to, okay, so that is a normal distribution where xn is the random variable and it's our kth Gaussian, and all the parameters in it will be fixed to our current best estimate, which is marked with an I there, a superscript I. So that means that that thing at the top is a normal distribution with the random variable xn. Okay, it's going to have mean, so it's the kth distribution, and it's our ith estimate of the parameters. So it's mean mu k with a superscript I, and then covariance matrix sigma k. Again, our ith estimate of it. So that's with the superscript I. And then we know that this thing, we were writing down pi's for this, but again, it's our it's pi k, and it's our ith estimate of it. So we have a pi k, and it's our ith estimate, and that's what we've got on the numerator. And then on the denominator, again, it's all this stuff. Okay, so I'll just copy this. Stick it down there. And let's say, oops, easy. Okay. And again, this is summed over k dash. Is equal to 1 to capital K. And these are now k dashes rather than k's. Okay, so we are nearly there. We have completed the expectation step. So the thing that we're going to maximize is given by this. Okay, so that's the thing we're going to maximize with respect to theta. So with respect to these, where this term is equal to that thing down there. So we're nearly there.